right. Good afternoon, everybody, or good morning, depending on what coast you're on. Welcome to another ABYC Thursday webinar. We're pretty excited. It's probably the most asked for topic we've had yet, which is lithium-ion batteries. So we're going to start with the basics, and the other guy you see on screen here is Dr. Denis Phares, who is the CEO of Dragonfly Technologies, or Energies. Did I get it right?
Dragonfly Energy.
Dragonfly Energy. Okay, sorry about that. So I'm going to do my basic, go through a couple things here, and then I'm going to turn it over to Denis. And I think you guys are going to learn a lot today. I'm pretty excited for this one. So weekly updates, as always, want to thank our presenters for doing this. And just as we get into more of these technical things and more manufactured products and topics that people want to see, I just want to let everyone know that we don't necessarily endorse or any of these products are considered compliant just because we're talking about them. So I think that's important. I know it's in past things we get very standards based, but there's some technologies like this that there just aren't the standards out there for. So keep that in mind, as we go through these. As always, we're working full steam ahead, all of us in our home offices and some back at the office in Maryland. And we're doing these weekly. I don't plan on stopping them anytime soon. We really enjoy doing them, and I hope everyone out there enjoys watching them. So we open it to registration to members first, so if you're interested, we get that out to them, and then it's open to the public. If you know any topics or presenters you'd like to see, please reach out. Let's see. All right, as always, we do give CEUs for these, so all you need to do is if you're watching this live, you'll get a follow-up email tomorrow with the link. Click that link, answer the question, and you will get your CEUs applied. If you're watching this on YouTube, there'll be a link at the end of the video to apply for the same ones. Questions, if you have any questions as we go through this, please type them in the box. As time allows, I'll be asking Denis them at the end of the presentation. And our trivia question will pop up at the end also. If for some reason you're not able to click the answer, just type it in the questions box and I'll make sure you're entered to win that. Online resources, as always, we got some great stuff going on. Fundamentals program, we have the textbook that's still free through the end of August. If you know any instructors, we have our ProctorU self-testing. So if you wanted to take one of our exams, challenge it, you can do that from the comfort of your home. And on our new learning management platform, we have some really great new courses that we're launching, and it's really user-friendly, so I encourage you to check that out. Online classes. So we continue to actually build out our online catalog through the end of 2020 since we canceled all in-person classes. So here's a short list of a few of them that are coming up. We have a gasoline, a standard, an electrical. There is still some availability in some of these classes. It's a really great way to take the class. We've actually seen a pretty decent uptick in passing rate through going through this format. So we actually do have a video posted that goes into a little detail on them on our YouTube page, and we're also going to include that link going forward in that email that comes out to you tomorrow if you're interested in learning a little bit more about how that works. And next week, we're going to be talking AC systems and troubleshooting with Ed Sherman. We just can't get rid of him. So we're really excited to bring him back. So keep a lookout next Tuesday for that registration to open up. So now that we got that out of the way, I am going to turn over control to Denis. He can introduce himself and get started here.
Thank you, David. Oh, perfect timing. I'm sorry. Let me just shut that off. Okay, my name is Denis Phares, and I'm very pleased to be here to talk about lithium-ion batteries. First of all, let me get my screen going here. A little bit about my background. I have a PhD in engineering, so I've worked on this topic for quite some time, not just lithium-ion batteries, but the production of electrodes using novel manufacturing techniques. So I kind of backed into this space through academia. I was a college professor for about 12 years before I quit academia and got a business degree and started Dragonfly Energy. So Dragonfly Energy is the lithium-ion battery technology company, and some of you may know our retail brand, which is Battleborn Batteries. And today I'm going to talk about, first of all, how lithium-ion batteries work, and where they're used. This is a topic that has been growing significantly over the last decade. It started off as laptop batteries, and then power tools, and into cell phones, and now electric vehicles, and more and more in terms of energy storage. They're starting to displace all kinds of energy storage devices. I also want to go right into addressing the safety concerns associated with lithium-ion batteries, because I think that's probably the #1 issue that we talk about with customers. And I also want to focus in on lithium iron phosphate, which is basically the only type of lithium-ion battery that allows you to make a 12-volt battery. We call these drop-in replacement batteries because they can more easily replace the lead-acid battery systems that most people have on their boats, or actually their RVs or other vehicles. And in light of that, I wanted to demonstrate a direct comparison between the function of these types of lithium-ion batteries with conventional lead-acid or gel or AGM batteries, and talk about some practical applications. So first of all, why did lithium-ion batteries become so prevalent? If you look at this plot, which shows basically the energy density versus the power density, the volumetric energy density versus the specific energy density by mass, you can see that both on a volume and mass basis, lithium-ion batteries are way more energy dense than lead-acid batteries down here, and nickel-cadmium batteries, and nickel metal hydride batteries. So you can see the progression. We started off using small nickel-cadmium batteries. Then I don't know if you remember, the Toyota Prius used to use nickel metal hydride, and now the whole world is using lithium-ion batteries. And lithium-ion batteries are so nice as compared to these other chemistries, because not only do they have the highest energy density, they also have no memory effects, which means you can charge it or discharge it partially or fully, and it doesn't affect the capacity. They have very low toxicity, especially lithium iron phosphate batteries, which don't contain any heavy metals like cobalt. And they also have the longest lifetime of any of these chemistries. Let me talk a little bit about how they work, because that is going to directly affect the safety concerns. So as in any electrochemical cell, there's a cathode and an anode. And in a lithium-ion battery, the cathode consists of a particulate lithium salt, usually a lithium oxide or a lithium phosphate. And on the anode side, it's usually graphite. And in this particular drawing, the black dots here are lithium ions. When you charge a lithium-ion battery, you can see these black dots, the lithium ions, move from the lithium oxide salt over to the graphite. And this process of incorporating into the graphite or into the salt is called intercalation. And basically what that means is that the ion itself is never actually reacting with the electron. So the electron is coming from the cathode to the anode, meeting up with the lithium-ion battery, but it's actually not reacting with the lithium ion, it's reacting with the carbon in the graphite. So the lithium ion never becomes a lithium metal. It never takes that electron and becomes lithium metal. This is as opposed to a lithium metal battery, which is not a rechargeable battery. And so this whole process of creating a battery where you can use lithium ions to intercalate between the anode and the cathode won the Nobel Prize in Chemistry this year. That was the inventors John Goodenough and Stan Whittingham. So this is, this was a groundbreaking discovery. I do want to note here that the lithium ions are moving back and forth through a diffusion process through a fluid, and that fluid is typically an organic electrolyte, and we will talk about that in a little bit. But first of all, I want to talk about the cathode, the lithium salts that are typically used. The first one that was used is lithium cobalt oxide, and those are prevalent in laptops and power tools and cell phones. And you can see the reaction here on the cathode side. The lithium breaks away from the lithium cobalt oxide. It releases an electron which goes through the charger to the anode, and you're left with cobalt oxide on the cathode. Another salt is lithium manganese oxide. This is the cathode that was used in the Nissan Leaf. The one that you might find in a Tesla, any one of the Teslas, Model S, Model 3, Model X, is lithium nickel cobalt aluminum oxide. This one has the highest capacity in terms of energy per mass, energy per volume. And I want to go right into the elephant in the room here. And I know that there's probably a lot of folks that are on this webinar because they want to hear how I address this topic, which is what happens when things go wrong. And I have to say, lithium ion batteries in general get a bad rap. This is a photograph of a burning Tesla. This is a photograph of the lithium cobalt oxide battery that was on the Boeing Dreamliner. And we all know there have been some high profile incidents where lithium ion batteries have caught on fire, including on boats as well. So I just wanted to address why that happens and how this can be prevented. Let me also add here that although you see lots of battery fires in cars, you probably don't see them as much in regular gasoline cars, even though gasoline is way more flammable and happens, adverse events happen a lot more often than with batteries. But batteries are new. So let's talk about what actually happens in the process known as thermal runaway. So we talked about the organic electrolyte. If the cell gets hot, then this electrolyte can evaporate and cause increased pressure and temperature inside the cell. In this particular pouch cell, you can see that it's bulging because of that pressure. We also talked about that plastic separator, which is typically a polyethylene polypropylene separator, which melts at around 80 degrees Celsius, so about 170, 180 degrees Fahrenheit. When that separator melts, the anode and the cathode can touch, creating an internal short circuit, creating more heat. Now, what happens at that point is, even though you've got this organic electrolyte that is potentially flammable, there's no oxygen yet. But if it gets hot enough, the oxygen can come off of the cathode. Remember, we've got lithium cobalt oxide, lithium manganese oxide, lithium nickel cobalt aluminum oxide. So when the oxygen comes off of the oxide, it can spontaneously react with the evaporated electrolyte, causing this uncontrolled reaction because you've got this continuous short circuit. And obviously, if you've got a large battery bank, that's something that you've got to be concerned about. So what causes these battery failures? If you have an uncontrolled charge, for example, you are over voltage. As I mentioned before, in normal operation, you don't form lithium metal. You just keep the lithium as an ion. But if you overcharge the battery and you put extra electrons onto the anode, now you've got an excess of electrons on the anode. It will react with the lithium ions that are already there to form lithium metal. And when you form lithium metal, you can cause what are called dendrites, which are almost like stalactites growing from the anode and through the electrolyte and into the cathode, and that can cause an internal short circuit. So that's why over voltage is bad. A similar thing can happen if you're charging the battery too fast at very high currents or at low temperatures, because at low temperatures, the lithium ions don't quite move as fast. They don't infiltrate the anode as fast. So you can end up in a situation where you've got an excess of electrons on the anode. And once again, you form lithium metal plating. Maybe you've heard that you can't completely discharge a lithium ion cell. That's true because on the anode of the cell, you have a copper collector. And when that copper becomes electron deficient because it has been over discharged, then the copper can dissolve into the electrolyte, when you recharge the battery, it will reform as copper, but not in a nice foil the way it was before. So you could potentially cause copper plating and an internal short that way. And then finally, you can have just a poorly produced cell. You can have impurities in the cell, you can have particulates in the cell, some sort of contamination that can either cause an internal short circuit or, at best, unwanted reactions that can, enhance the degradation of capacity. So how do you prevent these things from happening? Obviously, we wouldn't have as big an industry as we do now if we weren't able to prevent these things from happening pretty effectively. Step one is the cell quality. So, as the industry grew, there's been a whole lot of cell manufacturing facilities that popped up, especially in China. Some of them are top of the line, high-tech automated facilities, and some of them are not. And so the selection of cell quality is important. Also, just as important is the design of the battery pack, which consists of multiple cells that are in series and parallel to create the voltage and current capacity that you want. So as you look at your pack design, it's important that you have good dissipation of heat in case something bad happens, what actually happens to the pack if something bad happens to the cell. And if you're delivering a large amount of current, then it's important that that current is distributed effectively through your contacts and through your circuit board. So what is the circuit board? The circuit board is the battery management system number 3, and this is sort of the crux of it all. This is the device that will monitor the voltages and the currents and the temperatures and ensure that the cells are not being exposed to anything outside of their limits. So any lithium-ion battery pack really should have a battery management system inside or externally or in the system. This battery management system is critical in protecting the battery, not just for safety, but also just for longevity, because the lithium-ion batteries can last so much longer than conventional storage devices that it really behooves you to ensure that the cells are being protected for that reason alone. So what does the battery management system do? So at the very minimum, it should monitor the voltages, currents, and temperatures. And if it senses something that is errant in terms of the limits of the cell, it should have the capacity to cut you off in terms of charge or discharge. So I'm here primarily because I started helping with the development of standards for ABYC. I contributed to the lithium-ion subcommittee, and I was there to help during Standards Week. And a lot of the discussion revolved around the function of the battery management system. So I'm not going to go into everything we talked about in those committee meetings. I just wanted to basically provide my opinion of the minimum of what a battery management system should have for protection and longevity of the pack. We've already talked about how we should have some voltage protection. You want to prevent overcharging and you want to prevent over discharging. You also want to prevent the pack from delivering a current that is more than not just the cells, but the entire pack can handle. You want to have high temperature protection because we talked about what could potentially go wrong when temperatures get very high. You also want to have at least low temperature charging protection so you don't run into a situation where you're creating lithium metal plating on the anode. Finally, another very useful feature to have, and this is not an absolute necessity, but if you have a battery management system, you should at least have the capacity to balance the cells, which are in series. Cells in parallel will always share current and share the same voltage, but cells that are in series do not. So you have to have some extra current sharing or balancing mechanism that allows the cells to remain at the same SOC or state of charge. I also wanted to add here, even though we did not discuss specific standards in terms of third-party testing, there do exist standards that third-party test labs can allow compliance to. I wanted to talk about those a little bit because there is some confusion. For example, cells have their own listings, battery packs have their own listings, and battery management systems have their own listings. Lithium-ion cells can be tested to UL 1642 or IEC 62133. Battery packs for UL are listed to 2054 or 1973, both of which require 1642 as a prerequisite. So 1642 is not actually a pack listing. The IEC was an attempt to sort of create a listing that applies for both cells and packs. And then separately, the battery management system can be listed to 991 for the hardware, 1998 for the software, or 60730-1. These 991 and 1998 are not prerequisites for 2054 or 1973, but if you are not listed to those standards, then you require to be tested using fault conditions in your battery management system to ensure that even in the case of a failure, you don't create a dangerous situation. So those standards exist, and this is not a comprehensive list, but I did want to mention that. I also want to talk about another cathode chemistry, which is the one that a lot of companies focus on because it is really the 12-volt chemistry, and it's the most common in the aftermarket and probably the most common that a lot of the folks on this webinar will use, which is lithium iron phosphate. Lithium iron phosphate was discovered as a cathode by the same guy, John Goodenough, that won the Nobel Prize for discovering lithium ion batteries. The nice thing about lithium iron phosphate is, unlike the oxides, which shed oxygen at 150 degrees Celsius, the phosphate can hold on to that oxygen atom a lot more tenaciously, and it actually doesn't shed that oxygen until 350 C, so extremely hot, which means it's a lot easier to prevent thermal runaway from happening because it's kind of hard to get that hot internally. The problem with this chemistry was that it doesn't conduct electrons that well. But in 1999, there was another researcher at CNRS that discovered that you can coat these particles with carbon and it makes them electrically conductive. So this was a great discovery because now it actually works. And if you put 4 of these cells in series, you create a pack with a voltage that's 12.8 volts with a charging voltage of around 14.4 volts, which is right in there with a conventional AGM silver lead acid battery charging voltage. In addition to that, because of the resilience of this chemistry, they last thousands of complete cycles. So it's a really nice alternative. And we've used the term drop-in replacement because you can use these batteries to work with existing 12, 24, 48 volt systems. They can run those appliances and they can often be charged with the same chargers. That's what I'm going to focus on for the remainder of this presentation. So we've already talked about the longevity benefits of lithium ion batteries. Lithium iron phosphate in particular can last so much longer than a lead acid battery. This is a plot I took from the literature. This data is from the literature, so it's not mine. And you can see a lead acid battery, sealed lead acid equivalent battery lasting only a few hundred cycles. Obviously, you can take care of them and have them last a lot longer, but there's really no comparison in terms of longevity. A lithium iron phosphate battery will have an average degradation of only 20%, somewhere between 3,000 and 5,000 complete cycles. So in terms of stability, there really is no comparison. Let's talk about the comparison between the discharge curve between lead acid batteries and lithium iron phosphate batteries. What I have here is a plot of the discharge curve for 100 amp hour lithium iron phosphate and 230 amp hour 12 volt lead acid batteries. So this is sort of comparing apples to apples here, but the behavior is very different. So the lithium iron phosphate is in black, and the first thing you can notice here is that the black curve is a lot flatter. So during the discharge curve, the voltage does not sag in a lithium iron phosphate battery the way it does with a lead acid battery. The other thing you can notice here is you get about 100 amp hours with the lithium iron phosphate battery, regardless of whether you're discharging at 10 amps, 30 amps, or 50 amps. With a lead acid battery, you get very different results between 10 amps, 30 amps, and 50 amps. And this is the well-known Puchert effect that is lead acid batteries are much more susceptible. And basically what it means is the faster you discharge the batteries, the less total energy you get out of the batteries. Lead acid batteries suffer from the Puchert effect, and I will say these were brand new batteries. In addition, the Puchert effect is amplified for lead acid batteries when the temperature gets cold, and also as the temperatures get older. Sorry, as the batteries get older. I keep getting phone calls. Apologize for that. Okay. Next slide. Why else? What other benefits do we have compared to lead acid batteries? Why would you move to lithium iron phosphate batteries? So we talked about the fact that there is no memory effect. You can do a partial charge, you can do a complete charge, and in fact, it really is a true deep cycle battery. You can discharge the lithium iron phosphate battery to empty, and by empty I mean the cutoff of the BMS, where you're still within spec. Let's say you've got a 100 amp hour lithium iron phosphate pack. You discharge the full 100 amp hours and then recharge it, and you don't suffer a large penalty the way you do with a lead acid battery, where if you just discharge more than 50%, you can do some realizable damage in terms of capacity loss. We also talked about the voltage sag. Under high power applications, lithium ion batteries have a lower internal impedance, so they can deliver higher currents without the voltage sag. Now let's talk about battery charging. This is a similar plot, only this is for charging the batteries. The red curve here is the same two 6-volt batteries in series, 230 amp hours. The black curve is the same 100 amp hour lithium iron phosphate battery pack. There are two stages of charging here. You've got the bulk stage, where the voltage is less than the peak voltage of 14.4 volts, but the current delivery is maximum. And then you've got the absorption stage, or the constant voltage stage, where the voltage is at its peak and the current drops. And the main thing to note here is that the black curve is almost entirely in the bulk stage. Because of the lower impedance of the lithium iron phosphate pack, you can deliver the maximum current with a smaller voltage drop, which means that your charger is going to remain in the bulk phase, delivering the maximum current, charging current to the battery until almost the very end of the charging cycle. So you can see at the top of the charging cycle in black, there's a very short period of time where the charger is at its maximum voltage. The current drops very rapidly, and after minutes, the battery is fully charged. By contrast, a lead acid battery stays in the bulk phase for less than half the time. Then it hits the absorption phase, and the current drops very slowly until the battery is finally topped off. So with the same charger, you can charge a lithium iron phosphate pack faster than an equivalent lead acid battery pack because of this reduced impedance. And just in general, you can charge lithium ion batteries faster, but I will say the max charge rate will depend on your BMS and the components in your BMS, the spec of the cells and the pack construction, so consult with your manufacturer on that. So in terms of conventional charging, you've got the bulk phase, the bulk stage, the absorption stage, and the float stage. The bulk stage can stay largely the same. Your bulk voltage is somewhere between 14.2 and 14.6 volts, and you'll get a complete charge on the lithium iron phosphate pack. Now, absorption, you can see that the absorption stage was so small. Do you really need an absorption stage? Typically, the absorption stage is utilized by lithium iron phosphate packs for the balancing step. So we talked about internal balancing. You want the cells to remain at the same state of charge over time. And the way to do that is, as you get to the top of the charge cycle, when the voltage between the cells starts to separate, you can take the highest voltage cells and let them bleed through a bleed resistor. That's called a passive balancing mechanism, and have them meet the other cells as they come up to the same voltage. So absorption is a useful stage to keep. 30-minute, 60-minute absorption stage will ensure that on every recharge, your battery pack is going to stay in balance. So you can use the same charging algorithm or very similar charging algorithm to charge a lithium iron phosphate pack as for an AGM or lead acid pack. Now, do you really need a float stage? During the float stage, typically the voltage of the charger will drop down to about 13.6 volts, and it'll keep the lead acid battery at that voltage. Sometimes it goes into a maintenance mode at around 13.2 volts. The nice thing about lithium iron phosphate, it has a very low self-bleed. If you just disconnect the battery and let it sit for a year, you'll still have a significant amount of charge left in the battery. So the self-bleed of a lithium iron phosphate battery, depending on the usage of the BMS itself, is typically around 2 to 3% of its capacity per month. So you don't need to maintain the battery. You don't need to float it. It doesn't need to be trickle charged. But why do you have a float stage? Well, let's say you're plugged into shore power and you want to run all your appliances without running your battery. That's why you use a float stage. So you have your float, it'll run all your appliances off of shore power and your batteries will stay charged. As long as your float stage is somewhere above 13.4 volts, the batteries will stay charged for a 12-volt lithium iron phosphate battery. Do you want to stay higher than 13.8 volts? Do you want to stay at 14 or 14.4 volts? You may have heard that lithium ion batteries should not be left at a high voltage for long periods of time. I will say that for oxide-based cells whose internal voltage is higher than lithium iron phosphate, they are more susceptible to the damages created by high voltage than lithium iron phosphate. Lithium iron phosphate cells sit at around 3.2 volts. They operate at 3.2 volts, whereas the oxide, lithium cobalt oxide, NCA cells, they operate at around 3.7 volts and they're charged up to 4.2 volts. So they are a lot more susceptible in terms of premature aging at higher voltages than lithium iron phosphate. Having said that, we always recommend, if you've got a charger that's just going to sit at 14.4 volts or 14.6 volts, for days at a time, for a week, it's okay. But if it's going to be sitting there for months at a time, we would recommend that you disconnect the charger or disconnect the battery and just let the battery sit. There's no reason to keep it up that high. So conventionally, how is your house bank charged? A converter is a device that will create a DC voltage. Some of them just create a straight 13.6 volt DC voltage. That is not quite enough to put a full charge on a lithium iron phosphate battery, and it's definitely not enough to allow for the balancing to occur at the top of the charge cycle. So the newest converters from a variety of converter manufacturers, including PowerMax, Progressive Dynamics, WIFCO, they tend to have algorithms now that charge up to 14.4 volts before they come back down to 13.6 volts, and that works just fine for lithium-ion batteries. Solar charge controllers are typically very programmable, so it's easy to set your absorption times and your bulk voltages and your floats. Not all of them are. There are some that for some reason limit the bulk charging time. As long as you size your system correctly and you get about 5 hours of peak sunlight a day, as long as you can ensure that you're in full bulk mode for enough time to get your bank charged up, it's not that difficult to design your system appropriately. In terms of inverter chargers, they are becoming a lot more programmable. Victron, Xantrex, Magnum, etc. All have models now where you can easily set your voltages and your absorption times, your tail currents, etc., and your rebulk voltages as well. Finally, I want to talk about charging with alternators. Can a lithium iron phosphate battery charge from a 12 volt or 24 volt alternator? The answer is yes, they can. The voltages are adequate for that to happen. There are a couple things to consider. First of all, in point 2 here, rapidly shutting down the alternator current can cause a load dump or a flyback voltage spike that has been known to create, to damage devices and even damage a BMS or damage the regulators on the alternators themselves. There are ways to prevent this from happening. Alternators are supposed to be able to withstand a load dump. A lot of alternators they use avalanche diodes on their regulators, which are pretty resilient to load dump, and they can create a path for the current so that you don't get such a high spike. Another thing people do is they leave a lead acid battery as their cranking battery. If you've got a lead acid battery, it's almost like a big capacitor that absorbs any spike. You basically can't create such a high spike if you've got any sort of capacitance in the line, and lead acid batteries are like a big capacitor. If you don't have a lead acid battery, I know some companies make snubbers. Sterling Power makes an alternator protection device that we've tested in-house and observed a voltage cap at around 20 volts. You can isolate your lithium bank using a DC-DC converter from your alternator so that you don't have a hard cutoff in the case that the battery management system wants to cut off. You can also have multiple batteries, each with its own battery management system, so that you never have a hard cutoff. And then finally, folks are working on communication, either using CAN bus, NEMA, RVC, whatever, so that the battery can sort of spit out some information and say, hey, we're about to shut off. You might consider dropping the field on your alternator. Another thing to consider is, because of the lower impedance in a lithium iron phosphate pack, can it put extra stress on the alternator, which is always delivering its maximum current to charge the battery pack? And the answer is potentially yes. How do we deal with this? We've got approaching 100,000 units out there, the majority of which are charged by an alternator. We've worked with another company to develop a smart isolation manager to duty cycle the charging. So basically, give it a full charge for a while, then let it rest for a while, and give it a full charge on a duty cycle. You can regulate the current, for example, by a DC-DC converter, or you can regulate the alternator itself based on either the temperature of the windings or the current. So do you have to look out for some potential pitfalls? Absolutely, but you can absolutely charge your lithium bank from an alternator as well. So it's a system design question. Just want to go through a couple other nuances with lithium iron phosphate packs. Most batteries, including lead acid batteries, lose capacity in colder temperatures. I talked about how the Puchert effect is amplified with lead acid batteries. The same is true with lithium iron phosphate, but the loss of capacity is not nearly as drastic as it is for lead acid batteries. If you got a 100 amp hour lithium iron phosphate battery, you're getting about 90 amp hours at freezing and maybe 70 amp hours at 0 degrees Fahrenheit. We've done all sorts of in-house testing. It turns out that lithium iron phosphate batteries perform way better than lead acid batteries in terms of discharge at very, very cold temperatures. The problem, as we talked about before, is that they shouldn't be charged back up below freezing because of the potential for causing lithium plating, which could reduce the capacity of the pack. So, you know, it behooves you to have some sort of protection that either warms up the packs when it's cold. I know for us, for battle-borne batteries, we've got an external heating solution and an internal heating solution, and we do have an internal cutoff for charging if it gets that cold. And that's why, even though you can discharge the battery and it doesn't really harm the battery at cold temperatures, you don't want to charge it back up again. So a couple things to consider. High temperature operation it's a little different. If you're at very high temperatures, over 100 degrees Fahrenheit, you actually get more capacity out of the pack, but at the expense of reducing the cycle life. So if you're consistently over 100 degrees, your batteries are mounted in an engine room or something like that, then you could reduce the lifetime of the battery. Basically, the batteries have a natural chemical aging, and that is accelerated under higher temperatures. So, and obviously, if you're really hot, you know, over 100, 140, 150 degrees Fahrenheit, there's going to be a hard cutoff to prevent any further discharge, so you don't approach the temperatures that could cause melting of the separator, as we talked about before. Couple other nuances in terms of taking out your lead acid batteries and dropping in lithium iron phosphate batteries. Because of the flatter discharge curve, if you've got a voltage-based state of charge measurement device, it's not going to be accurate. It's basically going to think that you're full the entire time until you're empty. You can tune it, you know, there is some drop in voltage, but it's not nearly as pronounced as it is for lead acid batteries. So the thing to do is to use a shunt-based state of charge meter. That's, you know, that's standard now. So I don't think anyone should have a voltage-based state of charge meter. Some chargers will detect a voltage of 12.8 or 13.0 volts and say, wow, this is almost a full battery, so we're just going to sit in float mode. So that's where I kind of mentioned the rebulk voltage with inverter chargers. It's important to note that if you have, you know, if you measure a voltage of 13.2 or 13.1 volts, then you're basically at half state of charge. So you want to go back to a bulk charging mode there, and your chargers need to be tuned to know to do that. Low voltage cutout is an interesting phenomenon, because when you're below the low voltage of a specific cell, you want to ensure that you don't allow any more current to discharge from that cell, which means that you can't even measure a voltage from that cell, because measuring the voltage requires a very small current to be extracted from the pack. And if your BMS does not allow it, then basically you're not going to be able to measure a voltage, and you're going to get some meaningless voltage measurement. So some chargers, some solar charge controllers, some inverter chargers are not going to know there's a battery bank there and will not charge the battery. Some have gotten around that already, but in that case, you may need to trick it with a 12 volt jump start. Just let it see 12 volts, it'll kick in, and if you've got a battery management system that will allow charge when it's in low voltage cutout, then it will charge right back up again. And finally, we get asked a lot about what are the cranking amps, the cold cranking amps or marine cranking amps of our batteries. This is actually a meaningless value for lithium-ion batteries because the voltage sag is completely different. You don't get that voltage sag down to 7.2 volts, which is how you define cold cranking amps or marine cranking amps. The cells can typically deliver a huge amount of current, but the maximum current is typically set by the BMS. So we don't really say, well, here's the cold cranking amps, but here's what our BMS allows. So it depends on the manufacturer, it depends on the model of the battery. The question to ask is, what is the maximum allowable current and for how long is it allowed? Also, the batteries can be used to crank an engine. Note that if you've got a battery management system All that current is also going through the battery management system, so it's got to be designed appropriately. I've seen lithium iron phosphate cranking batteries on the market that are not designed appropriately, and I can't imagine how the FETs in those battery management systems can handle repeated cranks, but nevertheless, they're on the market. But it is important to realize that when you do crank your engine and you've got a millisecond of 900 amps or whatever, that your system can handle that. Also, because you don't have that voltage sag, the crank's going to look a little bit different to the starter, and I'm talking on the millisecond time scale. I will say that cranking with lithium iron phosphate packs is common. It's common with our products. But there are some differences that I think require a little bit more scrutiny in the lab. And I will leave it at that, and I'll be happy to entertain any questions for the next 10 minutes or so.
Right. Thank you so much, Dennis. That was really a lot of information, and I learned a ton there. So let's get our trivia question going while these questions pour in for our giveaway. And then we will start taking some questions. So if, you guys should see that pop up on your screen now. Kind of a gimme here, this one. All right, close that out and let's get to some questions. We have a few minutes here. Let's start at the top. Do you see a marine application for hydrogen batteries that are currently being used in forklifts by Amazon, Disney, and other warehouse environments?
Is this a question for me? I'm sorry, I can't see.
Yes.
This for some reason.
So I'm just going to read them off to you. Yeah, I'm reading them off to you, what I'm getting from people.
Okay. For hydrogen batteries, I'm assuming you mean hydrogen fuel cells. Correct me if I'm wrong, but hydrogen fuel cells it's a device that it's almost like a controlled combustion, where you've got an anode and cathode and a separator, and you're combining hydrogen with oxygen. You can make these with methanol as well, which I think is probably a safer alternative than with hydrogen. I personally wouldn't want a tank of hydrogen anywhere near me, but a lot of folks have been working on trying to make fuel cell cars, and as you probably know, lithium-ion based cars have completely displaced that notion. I would imagine that lithium-ion is going to continue to grow into the marine industry as compared to anything hydrogen-based.
All right. Lead-acid batteries cannot disconnect themselves from a vessel or charge system. What type of warnings do drop-in batteries have that can warn the boat operator of impending BMS disconnect?
This was a topic of, this was a frequent topic of conversation during Standards Week on this, and that is entirely up to the manufacturer. Obviously, internally, you can determine what the voltage of each cell is. You know what your BMS does, so you can send out, the manufacturer can send out any warning that it wants. If you just have a, lithium iron phosphate pack with a BMS that just disconnects, and there's no warning, then there's no warning. But you can measure the voltage, you can get a state of charge meter, and you can know where you are in terms of state of charge. So I think it's possible to create a safe system even without a warning system, but it's also possible for manufacturers to create a warning system if that is what is required by the standard.
All right. Should batteries be replaced after a lightning strike that is known to have damaged other electrical equipment, or is there diagnostic testing to confirm they are still fully operational?
There's all sorts of things that can damage a lithium iron phosphate battery, particularly the control board. I will say that we have had one instance of a lightning strike that damaged the board, and it basically was unable to deliver current through the battery management system. Are there diagnostics? Yes. If there's any damage, you'll probably see an increase in resistance in your system. Again, I'm not talking so much about the cells. If cells are damaged and you've got a series of cylindrical cells with a burst valve, you'll just basically see those cells take themselves out of the system, and you've got a lower capacity pack, a lower quality pack. If you've got single prismatic cells and you're in a situation where you've had an internal short, the batteries are discharged, it's not going to work at all. I mean, there's so many different things that could happen that in terms of what could get damaged during a lightning strike. And the result is not necessarily, a fire, but I think it's safe to say that you'll know by a change in how the impedance of the system, where the voltage sag is a lot more than you'd expect. That's always a telltale sign that something might be wrong with a contact, or with a FET, or even with the cells with reduced capacity.
Right. Are there different types of lithium-ion batteries required for house batteries versus cranking batteries, and what about venting of any gases?
It all depends on how the batteries are designed in terms of current delivery. You could have a battery that is typically a house battery, but they can be connected in parallel to deliver a huge amount of current to allow for a crank. I mean, that's often what we've done. But you can also create a cranking battery. There are different types of cells. Some cells allow for a 1C discharge rate or a 1 hour discharge rate. Some cells allow for a 10C or 30C discharge rate. So you can design a pack that has a very high power delivery capability in the cells, with a very beefy battery management system that can handle a large amount of current. So it also depends on the engine, and different engines have different cranking profiles in terms of current as a function of time. And again, this is like the tens to hundreds of millisecond time scale. These aren't cranks that last 10 seconds necessarily. This is like a spike that comes back down pretty rapidly. Yes, I would say the answer is yes. You've got cranking batteries, you've got batteries designed for cranking, you've got batteries designed for house banks, and then you also have ones that could be either, depending on how they're configured. And what was the other part of that question?
I have to go back. I'm not sure which one it was. Sorry, digging through here, but I think we're running up against the clock. I know you have a hard stop here, and appreciate your time. But I think one last question we can get you is, are there any specific battery testing tools that you'd recommend for those in the field working with these types of batteries?
Yes, the number one testing tool I recommend is a DC ammeter. It's so simple. You can get it at Home Depot. You got a battery bank, and you want to make sure that every battery pack in your bank is delivering current. Put your clamp meter around the cable coming from that battery and make sure it's delivering current. Some people may have an issue with a BMS or with a battery pack or with a connection or whatever, a fuse. Just go in and see where your current is going, where it's coming from, where it's being delivered. Everyone's got a voltmeter. That's great. Voltmeters are great, but a DC ammeter is something that we found a lot of our customers don't have, and I think it's probably the most useful tool to diagnose the system design, make sure you don't have too much impedance in one part of the system, or if you have a damaged battery potentially.
All right, I'm going to jump back on screen here. Unfortunately, we don't have much time for questions here. I know there's a ton of them. I can tell you this won't be our only presentation on this topic, so keep your eyes out in the next coming weeks about more specific install and things like that. And really, thanks again, Dennis. We really, really appreciate you coming out. and taking the time to talk to our members and all those folks out there who are paying attention. If you're watching this on YouTube, the link should be popping up to get your CEUs for this. And lastly, next week we're doing some AC troubleshooting. So we'll see you all next Thursday. We look forward to it. And thanks again, Dennis. Really appreciate you coming out.
You're very welcome. Thank you for having me.
All right. Take care, everyone.